So we're going to talk about arc length on a circle and some applications. So arc length is like, so here's a circle. So if I wanted to know this length here, then I want to know the arc length. That's what arc length means. And we can really determine the formula from arc length from the definition of radians. So just as a quick review, so we were just talking about radians. What does theta equal? So this is kind of important. Theta we said was equal to S over R. So I could rewrite this as theta over 1 equals S over R. And this actually reveals just the formula for arc length, because this S represents actually arc length. So if I take this formula and I manipulate it by multiplying both sides by R like you see here, then I can just cancel out the R's like you see, and so that I'm just left with S is equal to R theta. And yeah, so there it is. We have the arc length formula. So pretty simple to derive it. Now, it's very important to use this formula. Theta must be in radians only. So make sure you note that. So if you have degrees, you have to convert back to radians. So I said in another video that radians are like the new hotness. So this is kind of why. There's actually a lot of formulas where you have to use radians only. So you have to get very good at converting between the two. Okay, so let's look at a few examples. So I'll walk through this with you. A circle has a radius of 22.3 centimeters, so we want to find the arc length when the central angle has the following measure. So I'm going to give you the central angle, and then I'll just show you how to use the formula. So I've got 5 pi over 6 radians. So this is like your ideal scenario, because then you can just pop the formula, like boom, S equals R theta, and you just plug in the two pieces, right? So you've got your radius, and now you've got your angle in radians. So bada bing, bada boom, just plug the two numbers in, multiply them together, and if I multiply them together, I'll get 58.38 centimeters. So this application, or this, like when you have radians, this is pretty straightforward. Now, what if you have, say, degrees? If you have degrees, then you have to convert this back to radians, okay? So the thing I want you to remember is, so 180 degrees is equal to pi radians. I talked about this in another video. So we're just going to use this to set up our conversion. So I'm going to take 66 degrees and multiply by pi radians over 180 degrees. And so this way then my degrees will cancel out. So again, we talked about this, and we've been practicing this. Okay, so word of advice, when you multiply these things together, make sure you just leave this as a fraction. So your calculator should be able just to convert 66 over 180. It should be able to convert this to a simpler fraction. So if you don't know how to do that, maybe Google that or ask somebody, because this is a more exact number in your calculations. You do not want to convert this to a decimal yet, okay? So now I can use my formula S equals R times theta, because I've got everything in radians. So now, same radius, right, 22.3, and then this 11 pi over 30. So this is what I can multiply together to get my decimal. So I get 25.69 centimeters. Okay, so I just kind of flew through that, but I want to give you a second now to just kind of digest all of this. So I have one more example. So another circle with a radius of 15.22 centimeters. So what I want you to do is I just want you to pause the video and then just run out these two examples. Hit play when you're ready to see the solutions, and I'll show you the fully worked out solution. Okay, so the first one, nice and simple, right, because we already have radians. So since it doesn't say radians, we just assume it's radians. So I use the formula S equals R times theta. So I just pop in 15.22 times 3 pi over 8, and I get 17.93. So notice that this has 4 significant figures or significant digits. So we want to do the same thing down here, okay? And then for this other one, so we know we need to convert now degrees to radians. So I can take 125 degrees times pi radians over 180. And so again, you want to just leave it in that fractional form, 25 pi over 36 radians. I can use my formula and pop in the information. So 15.22 times 25 pi over 36, and I get 33.20 centimeters. Again, I've got 4 significant digits. Okay, so now I want to talk about a few applications with arc length. So the first application has to do with latitude. So you probably know, like, you know, if I said, oh, latitude, like you think it's like those lines on the map, but from a mathematical definition, so latitude is really the measure of a central angle where the vertex is at the center, or is at the Earth's center. So the initial side goes through the equator, and then the terminal side goes through a location. So you might want to write this down if you're taking notes or whatever. So what's cool about this is if we understand this, really like latitude becomes an application of arc length. So let's take a look. So let's say that the latitude of Panama City is 9 degrees north and the latitude of Pittsburgh is 40 degrees north. So we want to find the north-south distance between these two cities. And the radius of the Earth is 6,400 kilometers. So this will be relevant. And sorry, there's somebody outside doing some lawn work, so maybe you can hear that. Okay, so, all right. Anyways, so first, let's pretend this is the Earth. Here's the Earth, the north side of a piece of the Earth. And so I have to know that these cities are north and south of one another. So that's something that we're being told in the problem. So, okay. Panama City is 9 degrees, so it's going to be like south, and then Pittsburgh is north of it. So we're on the Earth's surface, and here's the location of these two cities. So that 9 degrees is talking about, so here's that equator, right? So from here to here, this is a 9 degrees, and then from the equator to Pittsburgh, that makes 40 degrees. So that's what the latitude actually means. It's talking about going from the equator, and then the terminal side going through that location, and here's that central angle. So hopefully that makes sense. Okay, so I want to figure out this distance here. So the question is, what is the central angle between now Panama and Pittsburgh? How do you find that? Well, so we're trying to figure out really then what is this angle here, and we can do that just by subtraction, right? 40 degrees minus 9 degrees to get 31 degrees. So that is this little angle in here. Okay, so now we have to convert this to radians. So you might be thinking, oh, I don't know where to go with this. Remember, we're supposed to be using arc length somehow. Is this supposed to relate back to arc length? And the one thing we know about arc length is that we have to use radians with arc length, right? So let's just go ahead and convert this to radians. So I take 31 degrees times pi over 180, and I get, I can't simplify this fraction any farther, so I'm just going to leave it as 31 pi over 180. Okay, so arc length. This right here, this length is the distance between the two cities, and so this is just arc length. Kind of crazy, right? Okay, so I'm going to use my little handy formula, r times theta. So this is where I need to know the radius of the Earth. So the radius of the Earth being 6,400 kilometers, that's where that information comes in, and then that arc length that we just, that central angle that we just found. So we multiply these pieces of information together, and we get 3,463 kilometers. So yeah, so we knew latitude, and now we technically just figured out the distance between these two cities. So that's kind of cool, right? But like, is this really true? Like, that was my first thought anyways. And I know I'm kind of a nerd, but I want to use the internet just to check, like, how close are we? So let's take a field trip. So we need to know the distance as the crow flies, as we say, because you don't want to, like, if you looked in Google Maps, right, there's like an ocean and you'd have to take roads and it'd be really hard. So you want the distance as the crow flies. So I just Googled a tool for that and found this website, Free Map Tools. You can just Google this. I was just curious to see if this actually works. So we've got Panama City. I'm going to type that in. And then Pittsburgh. Okay, so I plug in those two definitions, or locations, not definitions. And 3496. So notice that the land transport, so this would be like the Google Maps distance, so you would expect that to be farther, but if we could just fly direct, 3,496.589. That's like pretty darn close to what we found, right? So pretty cool. The reason that we're not exact is because we're using really like an estimate for the radius of the Earth. If we were using the exact radius, we'd be a lot closer. So this is pretty neat. Okay, so let's look at some other interesting, I'll say interesting, applications of arc length. Okay, so here's like maybe a surprising one. So a rope is being wound around a drum with a radius of 0.725 feet. How much rope will be wound around the drum if the drum is rotated through an angle of 42.25 degrees? Okay, so what are we talking about? A drum, so just think of it as like a circle. So it's a round shape, and we affix a rope to it, and then we're like rotating the drum around to wind up the rope. You see what I'm saying here? So the rope, so the drum is this radius, and the rope, let's say that we like tied the rope down or somehow we affixed it to this point, and so we've been rotating this drum around to this point, which is 42.25 degrees. So that's what this is talking about. So in looking at this, I want to know how much rope have we actually wound around, and like maybe you think, oh, I need to know something about the length of the rope. You actually don't, because all we really need to know now is we know the radius of this. This is just arc length, right? So from here to here, this is all just arc length. So all right, first things first, we need this formula. And we have, for our theta, we see that 42.25 degrees, so it's not right? So I think you could actually finish this problem. So what I want to encourage you to do is to pause the video, see if you can finish it, and then hit play. Okay, so I need to flip this to radians, so 42.25 degrees times pi over 180. I am going to leave that like this just to get a better number for my final calculations. It's kind of a mess of a fraction, but for our purposes, we'll leave it like that. So now I can just use my formula. So my S equals R times theta. So my R was that 0.7525. There was my radian measure. So just multiply those together. Bada bing, bada boom. So we've got 4 significant digits. So notice that's what I have rounded to. And so we are good. Okay, so for this last one, so this one's maybe a little tricky. So 2 gears are adjusted so that the smaller gear drives the larger one. If the smaller gear rotates through an angle of 150 degrees, how many degrees will the larger gear rotate? So you really need to know a little bit about the gears. So the smaller gear, you have to be told this. So the smaller gear in this case is going to be 1.5 centimeters. The larger gear will be 3.7 centimeters. So this is kind of a cool application. Like if you are going into like deeper engineering, you will definitely do problems like this. So it's a pretty standard problem. Okay, so let's talk about the gears. So first, of course, we're going to need radian measure. We know this has something to do with arc length, so let's just go ahead and convert that 150 to radian measure. So I've got 150 times pi over 180 degrees. So I'm just going to write that as the fraction 5 pi over 6. Okay, so the arc length of the smaller gear is really where we need to start, okay? So I know that my gear started at some point and it has rotated 150 degrees, and now I know that also the radius of the gear is 1.5 centimeters. So I can totally calculate like the arc length that this gear has gone across in that amount of time, right? Okay, so I take 1.5 times, so that was the radius, right? And then this number here that we just found. So I can find this arc length that my smaller gear has gone through. And I want you to just notice I am trying to leave this in a fractional format still. So I'm actually doing 7.5 pi over 6. Again, this will just get you a better number towards the end. So, you know, it's a weird looking fraction, but for this particular application, it makes sense to try to leave this in its fractional form so that we get a better answer at the end. So just remember this for now. We'll come back to this number in a moment. All right, so the tips of the gear teeth need to move at the same linear speed or they will break. So if you go into any engineering class, you talk a lot about this. We're kind of going a little bit more through the math part of this. So we need equal arc lengths in equal times. Okay, so what does that actually mean then from a math standpoint? So I start with this arc length formula, and now I want to focus on the larger gear. So we said we need equal arc lengths in equal time. So that arc length that I found earlier, that's where that's going to come in. So that arc length of 7.5 pi over 6, that's going to come in here. And now I'm going to try to relate that to the radius of this larger gear. Okay, so here is the arc length that we found, equal arc lengths in equal times. And now I want to relate that to the larger gear. So I use the radius here. So this now is helping us to kind of ensure that we have that condition met. And so the question was, how many degrees will the larger gear rotate? So now I've got everything set up, right? I just have to really solve for theta. Okay, so to solve for theta, I'm going to take 7.5 theta over 6 and then divide that by 3.7. So I just want to like show you like a trick with this, because you might be tempted to try to turn this into a decimal. So we're trying to avoid the decimal until the very last minute, okay? So instead what I'm going to do, instead of dividing by 3.7, remember an equivalent to dividing by 3.7 is the same as multiplying by 1 over 3.7. You see what I'm saying? So this just allows me to get, again, kind of stay in that fractional form, because this answer is in radians. What were we being asked? Degrees. How many degrees? So we need this in degrees. So now I have to convert this back to degrees. Okay, so now I take this answer times 180 degrees over pi, so my pi's will just drop out, and so I'm left with 60.8 degrees. And so I rounded that to 3 significant digits because my degrees were in 3 significant digits. Whew. Okay, so lots of examples, applications. I know they can be a little bit challenging learning how to set them up. I just want to mention I have another example video with even more applications. So wheels turning one another, gears turning one another. So if you are looking just to see a few more examples, I highly recommend that you check out my other application video. And otherwise, if you found this helpful, consider liking the video, commenting, sharing with a friend, subscribing to the channel. And otherwise, I will talk to you guys next time.